Section 6.5 is our final section, and that's the least squares problem. So we'll introduce the least squares problem along with a couple different methods of solution for the least squares problem, and then we'll end with an introduction to linear regression, or finding the line of best fit for a set of points in the plane, and we'll solve that problem as a least squares problem. So to get started, in practice, it's common that we might be seeking a solution to AX equals B, a linear system, when one might not actually exist. In other words, the system might be inconsistent. So that being the case, we might still want to find, an approximate solution. Maybe our closest thing to a solution is one way to put it. Now, this could come about if maybe we have a set of measurements, and some of those measurements are slightly inaccurate. We could end up with an inconsistent system pretty easily, actually, in practice. So it's pretty common to seek a least squares solution to such a system. Now, our idea for what the least squares problem is that we want to find an x that minimizes the distance from a of x to b, right? That minimizes the distance between the vector b and the vector ax. Okay, remember that a matrix A times the vector x is a vector. So we want to get as close to b as we can for some x value. So our problem is to find such an x, right? Now it turns out from our best approximation theorem of section 6.4 that this is really just the orthogonal projection of B onto the column space of A, but we'll see that in a moment. A solution to a least squares problem for the system AX equals B is an x hat, some vector x hat, such that the length between, or the distance between B and AX hat is less than or equal to B and AX for any x in Rn. In other words, we pick the best x hat, or the one that minimizes this quantity on the left-hand side, so that any other x that we pick would have a larger distance from B to AX. Now, with infinitely many x's to choose from, it might seem that this could be a daunting task. It turns out it's not actually too bad. So as we recall, and as I mentioned just moments ago, the closest point to the column space in A from B is the projection of B onto the column space of A, right? So that's what we're really looking for. AX is a vector that's in the column space of A, right? It's a linear combination of the columns of A. If B doesn't happen to be in the column space of A, in other words, there isn't an x such that AX is equal to B, well, the next best thing we can do, or the best approximation to B, is B hat, its projection onto the column space of A. And that's what we'll pick up in this discussion here. So again, as I said, AX is in the column space of A. Remember that matrix vector multiplication is a linear combination of the columns of A using x, the entries of x, as the weights. So we know that AX is in the column space of A, and we're trying to find the closest point in this column space of A to the point B. Well, here's the column space of A. It's typically represented as a subspace, which just looks like a plane. It's the easiest way to draw it, but it could be a larger space than that, or smaller. Now, if B is a vector, which is not in the column space of A, as drawn here, well, then its projection onto the column space of A, B hat, this point right here, is the closest point in the column space of A to B, right? So this is our, as good as we can get, as close to B as we can get from linear combinations of the columns of A. So we'll call this B hat the projection of B onto the column space of A, as we've done before. And then we note that, remember that this projection of B onto the column space of A, it's a linear combination of the vectors in column space of A. So it means that B hat is in the column space of A, right? The column space of A is the space spanned by the columns of A. So if B is equal to this, a linear combination of the vectors in column space of A, so B hat is in column space A. Also, the picture shows that as well, right? That the vector B hat drawn here is in that plane that's representing column space of A in this. We might call it a hyperplane to keep it generalized. But so that means that AX equals B hat is consistent, right? We can find an X in a linear combination of the columns of A to generate B hat, right? Since B hat is in the column space of A here. Now, we'll call that X, or that value X hat, okay? So then we have that AX hat equals B hat. We know that we can find an X hat that satisfies this because B hat is in the column space of A. So with this, X hat is a solution to the least squares problem, since AX hat, which is equal to B hat, is in the column space, is the closest point in the column space of A to the point B, right? So this B hat, which is equal to AX hat, is the solution to the least squares problem because it'll minimize the distance from B to the subspace column space of A. Now, that being the case, we can use the orthogonal decomposition theorem to see that the projection of B, which is B hat, has the property that B minus B hat is orthogonal to the column space of A. Again, that's this vector right here. B minus B hat is the vector that sticks up out of column space of A perpendicular and has terminal point at B's terminal point. So this is B minus B hat here. It's orthogonal to the column space of A, which means that it's orthogonal to every column in the matrix A. So that means that if we take any column, AJ, the jth column of A, and dot it, or take the inner product of it with B minus AX hat, which is B minus B hat, right, remember these are one and the same, then we know that their inner product should be 0. Now here I've written the inner product in terms of matrix transpose, right? So this is really AJ dot B minus AX hat, and when we write that as a matrix product, we have AJ transpose matrix as a matrix product times B minus AX hat. And that's true for every column. So for all AJs in the matrix A, every column of A, we have this is true. So this is really just telling us that A transpose times this vector B minus AX hat is equal to 0. And then if we solve for, well, if we distribute this A transpose across this product and add a transpose AX hat to both sides, we'll end up with this normal equation here to our equation AX equals B. So this is the normal equation to the equation AX equals B. And that's what we've just derived in it, though it looks clunky and perhaps useless at the moment, we realize this. The solutions, and this is what the theorem below says, the solutions of this system coincide with the least squares solution to this system. So this is our method of solution for the least squares system, right, is to find the solutions to this system, which is consistent, right? We've built it, we've argued that out, building this up. So we know we can find a solution to this system. And we also have seen now that the solutions of the least squares problem coincide with this, right? Remember, X hat here was the least squares solution to this problem, since its AX hat is equal to B hat, which is the projection of B onto the column space of A. So we can find this X hat, and this using normal techniques, right? We just need to multiply by A transpose on both sides and then solve the resulting linear system. And then that same X hat that we find as a solution to this system is the solution to the least squares problem of AX equals B, the one that's inconsistent. So that's a nice tool to have. And it doesn't assume much about A whatsoever, right? We can take A transpose, multiply it by both sides of AX equals B, and come up with that new system and solve for X as a linear system, no matter what, really. So this is a pretty powerful solution. We'll see some other ones that we can use as well that depend on some properties of A. But first, let's implement this in an example. So we're asked to find a least squares solution to the inconsistent system AX equals B. So it might be worthwhile to actually see that this is an inconsistent system, right? So in other words, if we write the augmented matrix A and augment it with the column B, so we'll have a 3 by 3, and we put it into row echelon or reduced row echelon form, we should see that we get an inconsistent system. And in fact, really, this one's really easy to see, because if I look at the middle line here, oh, that's actually not a problem. So maybe I'll scrap that. But if we consider that this would be 1, 0, or 1, 0, 1/2, this would be 0, 1, 0. We can zero out both of these values. And when we're done doing that, this 11 in this bottom row is not going to be 0, though these 1s in this bottom row will be 0. So if you put this augmented matrix into reduced echelon form or row echelon form, you'll find that it is in fact an inconsistent system. You have zeros leading up to a non-zero on the right. Now, you don't really need to check that, because it turns out that if you run the least square, if you find the least square system solution to any system, then if it is consistent and has a solution, then the least square solution will be the actual solution. You'll find the actual solution of this. Now, you might not want to do that because it is extra work. We have a lot of extra baggage here before we get to work on this system. We have to calculate A transpose, and we have to multiply both sides of AX equals B by A transpose. So nonetheless, let's get to work on this example. So A transpose is this matrix. A transpose A is this product here, and we end up with, note that it's a 2 by 3 times a 3 by 2, so our result is a 2 by 2. A transpose B, well, that's this matrix again, times the column B, and this is a 2 by 3 times a 3 by 1, so we get a 2 by 1 here. Now this is our A transpose A matrix. This is our A transpose B right-hand side. So our linear system is A transpose A times X, so this times X, is equal to A transpose B, which is just this vector here. So as an augmented system, it's really just this coefficient matrix with this augmented to the right-hand side, and that's what we have right here. So there's our linear system that comes from this, and this is solved in the way that we're typically used to, right? We can, since it is 2 by 2, we could have thought about inverting this 2 by 2 matrix and multiplying B by the inverse of A. In this case, what I've decided to do is to use a row echelon or reduced echelon form. So that follows the steps given here. And what we arrive at is, it looks like x1 is equal to 1 and x2 is equal to 2. So our solution vector, or our least square solution, is the vector x1 equals 1, 2. So that's as close as we can get, right? So that's the best solution we can come up with for AX equals B in this inconsistent system. Note that had we used another method, we'd end it saying this thing is inconsistent, doesn't have an exact solution, but it does have an approximate solution. And it turns out that AX, whatever that comes out to, multiply A times X, is as close to this B as we can get. In fact, it's the projection of this vector B onto the column space of this matrix A. Nonetheless, this vector X we found is our least square solution to AX equals B, because it's the solution to the normal equation, A transpose AX equals A transpose B. And that's really it for these problems. This is the way that they're going to work. Now, of course, conceptually, I guess that's not too difficult, but it could be a little tedious. We've got to do some matrix multiplications before we solve a linear system. So there is a little bit of extra work. If it happens that the system's consistent, well, then the best idea is to just solve it in the old way and not run it through all the least squares trouble that this would bring about. So find a least square solution of AX equals B for matrix A is equal to this. Looks like a 6 by 4, and B is equal to this 6 by 1 vector. So again, it might be worthwhile to augment this column against A just to check that it is in fact inconsistent. I think that we can see that that's the case. If we look at these bottom 2 lines, or really any 2 lines that have the first 4 entries matching, say like the first 2 rows as well. But if I look at the bottom 2, I can zero the bottommost row here with the row above it, and that will make all of these terms in the beginning here 0. But then this is 1 minus 5 on the right, and that's a -4, which is not 0. So I'll have all zeros here, and then a -4 here. That's an inconsistent system. Again, you don't have to confirm that it's inconsistent if you're asked to just find the least squares solution. But in practice, it's probably worthwhile to make sure that you're dealing with an inconsistent system before you do all the work of a least squares solution. So again, the least squares solution to an inconsistent system like this coincides with, in other words, is the solution to A transpose AX equals A transpose B. So what we need to do is we need to determine the system that this normal equation represents. So in order to do so, we need to find A transpose A. So we've written A transpose here, multiplied with A, it's this, and the result of that matrix product is this 4 by 4, right? We have a 4 by 6 times a 6 by 4. So the middle dimensions combine, or sort of fall out, and we have 4 by 4 as our resulting dimension of this product. Now, on the other hand, what do we see? We have A transpose B. This is a 4 by 6 matrix times a 6 by 1. So we should get a 4 by 1 matrix, or 4 by 1 vector, or 4 vector out. When we carry out this product, we get this 4 by 1 vector on the right. And now our system, A transpose AX, well, here's the coefficient matrix, and here's the right-hand side. So we just augment that 4 by 4 with this 4 by 1, and then we go about our business in the usual way. Again, I decided to use reduced echelon or row echelon form to solve this system. It looks like I arrive at reduced echelon form, since all of my leading ones, pivot positions have zeros above as well as below. And when I solve for this, I see that x4 is free. So that's an interesting thought. We have a free variable in this solution, whereas the other problem had a unique solution. And looking further, when we solve for these, we realize, so we have a homogeneous part and a non-homogeneous part of our solution. Here's our non-homogeneous part of the solution, and here's our homogeneous part of the solution. So what we end up with, ultimately, if we look at this solution after we pull it from these equations, this is our parameterized vector solution down here, we see that the solution to the least squares problem is actually a line, which is not impossible, right? It just leaves us now with one last choice. We found a least squares solution. This line happens to be the closest thing to the column space of A, or the closest thing to B, the vector B, in the column space of A. So it can, and this is perfectly feasible that this might be the case. We might get a solution that is a line and not just a single point, or it could be an even bigger space. There could be a plus a vector times a parameter S, and now we're talking about a plane, which is the set of solutions that's the closest point in the column space of A to this vector B that we started with. So a big question then is, how do we know what to expect for our solutions? Well, you'll notice that something interesting about this matrix is that if I look at the first column, it's actually a linear combination of the second 3 columns, right? If I add the second 3 columns together with multiples of 1 times each, then I form the first column. There's a linear dependence among these columns. And that's a good hint as to why we don't have a unique solution, right? We have unique solutions to, well, it's a good hint, but it doesn't quite get us there, because remember, we weren't solving the system AX equals B, we were solving A transpose A equals A transpose B. So we're an operation removed from being able to consider the linear independence or dependence of the columns of A in terms of the system we actually solve. But it turns out what our intuition might guide us toward will happen to be true. Okay, so we'll see that on the next page. But before I get there, let's just have a look back. Notice that these 2 columns for this matrix were linearly independent, and we ended up with a unique solution to the least squares problem. Now that's just more evidence for what we're about to see in this theorem here. So if we have an n by n matrix A, then the following statements are equivalent. When the equation AX equals B has a unique least squares solution, remember that's our approximate solution, for any B in Rn. So this is equivalent to the columns of the A are linearly independent. Well, we just talked about that. We didn't see why, but we we just saw evidence in two separate cases where if the columns of A were not linearly independent, we did not have a unique solution for the least squares problem. And we saw that we had a matrix A with columns that were linearly independent, and we did have a unique least squares solution. These two equivalences are, these two facts or statements are also equivalent to the matrix A transpose A being invertible as well. And then when these statements are true, in other words, when any one of these statements is true, which means that all of them are true, then X hat is equal to A transpose A quantity inverse A transpose B. Remember that A transpose A is actually an n by n matrix. A is m by n, so A transpose is n by m. N by m times an m by n matrix leaves us with an n by n. So we always have a square matrix when we have A transpose A as a product. So it leaves it as a candidate that could have an inverse, even though A being m by n, where m and n are not necessarily equal, does not have an inverse, or we can't even talk about it having an inverse. So that's a nice fact to keep in mind as we look at this. It turns out the key to this proof is the following: to show that the null space of A is equal to the null space of A transpose A. Now, A transpose A is n by n. It has n columns. A is m by n. It has n columns. Note that we talk about the columns of A, and which there are n of them in terms of their linear independence or dependence. So if we just inspect something real quick, if we see that AX equals 0, so if we let this be the case, then that implies that A transpose times AX, well, AX is equal to 0. This is equal to A transpose times 0, since AX is 0. And A transpose times 0 is just a matrix times the vector 0, and we get 0. So this means that if there's a vector X such that AX equals 0, then A transpose AX is 0 as well. So any vector in the null space of A is also in the null space of A transpose A. So this gives us a subset. Null space of A is a subset of the null space of A transpose A, because any vector that's in null space of A ended up being in the null space of transpose A. Now, going the other way to prove equality here, we let there be an X such that A transpose AX equals 0. Now, if we multiply both sides of this by X transpose, and we'll see why in just a second, this is the trick to this part of the proof, then we have X transpose times 0 on the right-hand side, which is just 0. So when we get here, we'll see that this is just 0. But it turns out that X transpose A transpose is AX quantity transpose. Remember how to take the transpose of a matrix product. It's you reverse the order and take the transpose of each item. So this is actually, remember that AX is a vector. So AX transpose times AX, that's just the inner product of the vector AX with itself. And so this equality is telling me that the inner product of the vector AX with itself is 0, which means that AX must be the 0 vector. Remember, that's a property of inner products that we saw back in section 6.1. So that tells me that AX is the 0 vector. Okay, so what that means is that if X is in the null space of A transpose A, then X is also in the null space of A. So now we've got the set inclusion going the other way. So if X is in this space, it's also an element of this space, which means that this set is a subset of this set. Each set includes each other, so the sets are equal to each other. And once we have this fact nailed down, might not be clear, the theorem says nothing about the null space, but remember our rank theorem and remember our invertible matrix theorem. We've got a lot of equivalences and a lot of things that tell us about and give us some information about a matrix A or A transpose A based on their null spaces. So one of those things being this: if the matrix A transpose A is invertible, then that means that its null space is the 0 vector, which means that the null space of A is just the 0 vector, only the trivial solution, which means that the columns of A are linearly independent. Now the rank theorem would tell us the same, right? The null space of A transpose A being 0, thanks to A transpose A being invertible, it'll have nullity 0, right? The dimension of its null space is 0, right? So it has rank n. Well, the null space of A is equal to the null space of A transpose A. So the null space, the nullity of A, the dimension of A's null space is also 0. So A has rank n. If A has rank n, then A has n linearly independent columns. So we see the equivalence back and forth between these two. Now, AX equal B having the unique least squares solution, this is really the same as A transpose AX equals A transpose B, the normal equation, having a unique solution, right? So this tells me that A transpose A has a unique solution X for any B that we plug into this. Well, that means that A transpose A X has full rank. Rank is n, and the rank theorem tells me that the nullity must be 0. And then that lets me know that the nullity of A must be 0. So then A must have columns that are linearly independent. And so that's the heart of this result. And the crux is really just recognizing that these two matrices share null spaces, have a null space in common, and that gives us the sort of the linchpin to move between any one of these equivalences. So I guess the last thing to note is this: we couldn't just talk about A inverse in this problem because A is m by n. Right? So nowhere does it mention A having an inverse. It talks about A transpose A having an inverse. Remember, A transpose A is square, whereas A is not necessarily square. So the best we can talk about is A having linearly independent columns, or we can speak about A's null space as we did down here. So that's really the connection between the all these equivalences, is that they share a null space. Nonetheless, these are nice facts to have lying around now. Now we can form expectations for least squares solutions based on this property of A. Also, if these things are true, well, then of course we can write down A transpose A's inverse, and we could find our solution X hat to the least squares problem by calculating this: A transpose A's inverse times A transpose B. That might be a lot of work, but it is yet one more way we could use to solve these problems. So other methods of solution here involve a matrix A which has orthogonal columns. So if A is an n by n matrix with orthogonal columns, then the least squares solution to AX equals B. So supposing that AX equals B is inconsistent, so the best we can do is find the projection of B onto the column space of A. Well, note that a projection of B onto A is really the weights, right? This is the linear combination of the columns of the matrix A, which all happen to be orthogonal. So the projection is this formula right here, as we've used in previous sections. Well, this is the linear combination of columns of A1 through AM. Well, this will form our vector X. We just pick up each of these coefficients in front of each of our vectors and our column vectors of A, and that's the solution: A times this X, right? So this expression right here is really A X hat equals B hat, with X hat being equal to these weights that are written here. So the first entry of X hat is this coefficient of A1, down to the mth entry of X hat is this coefficient here in front of AM. So this sort of simplifies the problem, right? We could, if we knew we had a matrix A with orthogonal columns, then we could simply find the solution by just picking up the coefficients of this projection calculation, and that would be our least squares solution, this X hat off to the side. So that's one way to do it. We don't always have an orthogonal matrix, but or a matrix with orthogonal columns, but we do have a way to take a matrix A, which has linearly independent columns, and form a decomposition. This is the QR decomposition. So this method that we've just talked about here tells us that, well, if we can turn A into a matrix that involves an orthonormal matrix like Q has columns which are orthogonal and moreover orthonormal even, we can actually probably use this decomposition of A to solve the least squares problem as well. And that's what the theorem below is telling us. So if we have an n by n matrix with linearly independent columns, remember this is necessary in order to have a QR decomposition from section 6.4, then we'll let A equals QR be the QR factorization of A, which means, remember that Q then is an orthonormal matrix, whose columns span the column space of A, right? So the columns of Q are an orthonormal basis for the column space of A. And R is an upper triangular matrix with positive entries along its diagonal, which means that R is an invertible matrix. So we can talk about R inverse. It's an n by n invertible matrix as well. So whereas the matrix Q is an m by m matrix, I believe. Let's see. We have to, well, we'll have to remember, we can look back to the QR factorization for the dimension of this, but R inverse, R is a square matrix, and it's a square and triangular matrix with positive entries along its diagonal, so it is invertible. That's the key point here. So for any B in Rm, the equation AX equals B will have a unique least squares solution given by X hat equals R inverse Q transpose B. Okay, so the reason why this works is really because once we decompose A as the product of an orthonormal matrix Q and some triangular matrix R that's invertible, then, well, we can find the orthogonal projection of B onto the column space of A. That's what this Q transpose B is doing. And the R inverse is really just the rest of this decomposition tagging along to make sure we have all the details straightened out. And that's a really, really rough way to describe this. But if the proof of this theorem is pretty easy to see. So that's really what I'll do. If we just observe that A times X hat, if X hat is equal to this, right, is equal to, well, X hat is R inverse Q transpose B. So we write this down. And then this is equal to, remember that A has decomposition QR times R inverse Q transpose B. Now R times R inverse is the identity matrix. So that cancels out. We're just left with Q times Q transpose, as we see here. Now Q times Q transpose, the thing that we have to remember, since Q has orthonormal columns, Q times Q transpose is the identity matrix also. So this is the identity matrix times B. So this is just equal to B. So the X hat, our least squares solution, is found by this formula right here. We can apply R inverse to Q transpose B. And that really, again, the heart of what's going on here is the fact that Q transpose B is really it's helping us to find these coefficients that are to make up this vector X hat that solves the least squares solution, the coefficients for the linear combination for the vector projection of B onto the column space of A. Okay, so nonetheless, we can use this method. What the method will entail is the following. We'll be given a matrix A and a vector B. We'll be looking for AX equals B's solution. We'll be looking for a least squares solution because that system is inconsistent potentially. What we'll have next is we'll need to find the QR decomposition of A. So this might not be a very practical solution. This is kind of lengthy, right? We'll have to form an orthonormal basis of column vectors that make up the matrix Q. And then we'll have to find R, and we'll recall how to do that from section 6.4 in our example. We'll have to calculate the matrix R, then we'll have to calculate the inverse of the matrix R, and then form this product in order to calculate x hat. It's just probably not as efficient as the normal equation method from previous to this, but it is an interesting way to see it. And depending on your purposes and what you might be doing numerically with something, this might be a more appropriate technique. So let's run this through as a full example. This will be fairly long, but all the details have been worked out. So I'll probably move quickly in the places that should be just calculation. So if possible, use the Qr decomposition of A to find the least squares solution of AX equals B, for A being this matrix and B being this vector. Now again, a couple things we could start with. In practice, you might just try to solve this system directly, right, as just the augmented matrix, and then know for sure that it's inconsistent before you resort to a method like this. Where this, again, like the normal equations did, even if the system is consistent, it will turn out that the solution that we find will be the solution we would have found otherwise too. So this is just possibly an overkill method if we don't have an inconsistent system. So if we're going to use the Qr decomposition method, well, we need it. It only works if the columns of A are linearly independent, right? A only has a Qr decomposition. That's why this says if possible. We can only decompose A as a Qr decomposition if A has linearly independent columns. So one thing you might want to check out of the gate is whether or not these three columns are linearly independent by putting it into echelon form. It turns out if you started to do this process and you weren't able to get a third or second or whatever orthonormal basis vector, then you would see the process would essentially fail. You'd have a column of zeros somewhere, or you have something undefined that would halt this process altogether, and you'd realize that it's not possible to solve this with a Qr decomposition because the columns of A were not linearly independent. So that said, if you need to do a problem like this, you'd probably just begin it as is. So we need to decompose A as Q times R. So we need to form Q first. We need to create the matrix Q, which arguably might be the bulk of the work. Remember, this is a matter of Gram-Schmidt, right? So we need to form an orthonormal basis or an orthogonal basis of these column vectors through the Gram-Schmidt process. So the first vector, U1, is just going to be the first column of A. So we get the first one for free, as always. Now U2, this is going to be our second vector in the orthogonal basis that we're building. So this is X2, or A2, I guess, and given this notation, minus A2 dot U1 over U1 dot U1 times U1. So this is our normal formula for the Gram-Schmidt process. The vector that comes out of this is off to the side. That's this 1, -1, -1, 1. So we have U1, U2. These are now our two orthogonal basis vectors. You might want to double check along the way that these two vectors are orthogonal to each other by taking their inner product and seeing that that's equal to 0. So far, so good. Now to find U3. U3, we take the A3, the third basis vector in our original basis, and we subtract from it A3 dotted with U1 over U1 dotted with U1 times the vector U1, right? That's the standard formula here. And this is minus A3, remember this vector, dotted with U2. Do not use A2. Go back and use this vector, U2, and then divided by U2 dotted with U2 times the vector U2. I only use my vectors in here one time, except for A1, which shows up over and over as the U1 vector because we got that one for free from there. Now, when I simplify all of this, I get this vector. So again, we might want to check that U2, U3, or U3, U2, and U1 are all orthogonal to each other by doing their pairwise inner products. You'll find that that's the case. All these inner products are 0 for these pairs of vectors. So now we have the columns of Q, except we need to normalize them. In other words, they need to be unit vectors. Notice that the length of each of these vectors is really each entry squared and added up. So that's just 4 in all cases, and square root of that, so that's 2 in all cases. So we divide all 3 vectors by 2, and each of these column vectors now becomes as follows. U1, U2, and U3 have been normalized to these vectors. We find that if we took the length, calculated the length of each of the vectors in Q here, we would have 1 for each of them. We could also check that their inner product, each pairwise product of these columns, is 0, so that it is orthogonal. But this is in fact the case. So now we have Q. Remember that once we find Q, that if we're talking about a decomposition, A equals Q times R, remember Q has the property that Q transpose is equal to the identity matrix. So Q transpose times A here is equal to Q transpose times QR. And if we're trying to solve for R for this, we just get R out of the right-hand side. So R is equal to Q transpose A. So now we have a means of calculating R. Right? You don't have to run this every time. I was just reminding the viewer or the reader where this formula comes from. So this is the formula you use at this step, and that's where it comes from up above. So Q transpose is just the transpose of this matrix, written right here, times the matrix A, our original matrix. And what we get out of this is this triangular matrix, upper triangular, right? Everything below the main diagonal is zeros, with positive entries along the diagonal. Right? That's one expectation, and it's a check that you should have in here. Be sure that you have all positive entries along the main diagonal of this matrix. And we do in this case, so that kind of pass the check, and we don't worry about looking for errors we might have made at this point. Now, next up, we need the inverse of R, because we need to calculate X equals R inverse Q transpose B. Remember, B is this matrix here. We'll finally use that once we have R inverse. So we need to invert R. And I did this with the cofactor formula, right? Or the adjugate formula. So here's the determinant of R, 1 over that determinant, rather. Remember, the determinant of a triangular matrix is just the product of the diagonals. And then I took the adjugate of this matrix, which is given here, except I haven't transposed it yet at this stage. And then I multiply by 1/8 and transpose this matrix, and I now have R inverse. Now, it doesn't matter how you want to invert this matrix. You could do this augmented with the identity matrix in R3 and put it into reduced row echelon form. You'll get the same thing that I've got down here if everything goes correctly, and we'll be on our way. Now we use R inverse times Q transpose times B to get our solution to the least squares problem. And that's just a matter of a matrix product, matrix times vector product. And that's what happens on this page. So here's X hat, here's R inverse times Q transpose times B. And it doesn't really matter which order you carry this out in. I think I elected to multiply this matrix times this vector to keep my number of calculations and the amount of stuff I wrote down a little bit more, a little smaller, a little more succinct. And R inverse times the result of Q transpose B is this, and we arrive at X hat being equal to this vector. And this is our least squares solution to our original system. So X hat is this vector 10, -6, 2. We want to go back and have a quick peek. Does this fit the dimensions at least, or the size of the matrices involved? This is a 3x1 vector. So AX, this matrix A times a 3x1 is going to leave us with a 4x1 vector B. Yeah, okay, so it looks like it would work. So there we have it. We have our least squares solution to this system. Now, you'd find that it's not an exact solution to it, right? I can't go, and this is the case for any least square solution when the system that we started with was inconsistent. If I plug this X hat into this AX equals B, in other words, multiply A times that X hat that we found, I'm not going to get this exactly. The output I'm going to get is B hat. And B hat is the closest thing in the column space of A to this value B. It's the closest we can get to achieving this right-hand side of B for this system. So keep that in mind. Don't check your least squares solution by plugging them back into this matrix right here and seeing that you get this vector. you're not going to get it, unless, of course, the system was consistent to begin with, and you could have just used an augmented matrix technique to do that. So that's it for the least squares problems. We've seen a couple of methods now. I hinted at this one. If we know that the vectors of the column vectors of A are orthogonal, we could solve a problem this way. And if not, more generally, if we just have linearly independent columns in a matrix A, then we can use the QR decomposition, which relies on this essentially, or kind of based off of that to solve it. But I think I would recommend overall to just stick with the normal equation solution. I don't think that you'll be constrained, at least not on any exam or quiz, to use one method over the other. Well, potentially so, just to practice, just to demonstrate the QR decomposition method. But if you have a choice, I would suggest using this in most cases. So now let's look at one last application here. This is sort of the culmination of all of this work. What might we do with the least squares estimate? Okay, so this example comes from machine learning, where it's common to try to make predictive models for a given set of observations or for data. Right? One of the most fundamental predictive models is linear regression. Okay, so in other words, linear regression is the task of finding a line of best fit when we have a set of data points x1, y1 through xm, ym living in the plane here, and they're not collinear. Even though if we look at these points x1, y1 through xm, ym, they kind of have a trend, right? They're more or less following this line. There's just noise. They're not all exactly on the line, so they're not all collinear. So this is just a fundamental problem in statistics, and also in the machine learning as an extension of statistics, is to find this regression line. So this regression line is the line of best fit. It's the one that minimizes the distance between these points and this line. So what we're trying to do is minimize the error from our line to our points. So obviously I could draw another line that would estimate these and it would look like this, and that's not a very good line of best fit, right? It's not really a matter of guessing to come up with a line of best fit, or this trend line, as some might call it, or the regression line. There's an exact method to it. What we're trying to find is a line whose equation is y equals beta naught plus beta 1x. So beta naught is our constant, it's our y-intercept, and beta 1 is the slope of this regression line. So what we can use, clearly, these points cause this to be an overdetermined system, right? So there's noise here, right? Not all points end up on this line, and in fact, there's no straight line that goes through all of these points at all, right? That would have to be a broken sort of zigzagging line, like this polygonal approximation, or that would be called interpolation if we're dealing with polynomials. But that's not what we're interested in. It's not a very good predictive tool. It will overfit. We're trying to capture the trend here with the least error possible. So here's some notation. We don't know these coefficients, beta naught and beta 1. That's our goal. So if we write beta naught and beta 1 as a vector, a 2x1, and then if we write our x as a matrix, so this x we're writing as a matrix, 1x1, 1x2 down to 1xm, well, and then y is y1 through ym, what we realize is that if we take this matrix times this vector, beta naught, beta 1, that's this product right here, we're actually getting our output of y, right? So let me look at the first row potentially. So I do the first row of x here times this vector, beta naught, beta 1, and what I get is 1 times beta naught, so beta naught, plus x1 times beta 1, and that's equal to y1. So what we're trying to do is find beta naught and beta 1 such that the error, the difference between this product, beta naught plus beta 1, x1 and y1, is minimized. Okay, and that's minimized for all of these. So it'll turn out, since these things are not on, these points are not all on the line, this is an overdetermined system. It's inconsistent. And I'll show you in the example here where we can see that a system is inconsistent when we're coming up with a linear regression line or a regression line for it. So in this case, that might not be quite apparent yet. So what we're looking for is a least squares solution to this, x times beta equals y. Now, beta is playing the role of our unknown variable, or our unknown vector, rather, beta naught and beta 1. We're trying to find those two parameter values so that we can write our line down in this form. And we're going to use all of our information, x1 through xm, y1 through ym, in order to pick our best fit line. So note that since all those points are not collinear and the system's inconsistent, the best we can do is minimize the distance from y to x times beta. Right, that's what I was saying before, or beta hat being the projection of beta onto the space, onto the column space of x. Okay, so, or y hat. So x times beta hat is y hat, which is the projection of y onto the column space of x. It's a little confusing with the variables, but you see that everything matches up once you match the variables correctly to what we did previously. This system, this least squares problem, has solutions, again, as we saw previously, that coincide with this normal system, or this normal equation here, which is x transpose x beta equals x transpose y. And this is, in fact, the textbook method for solving for the coefficients of a linear regression problem. Now, it turns out in practice that it's more numerically sound or efficient to use other methods, but at least in linear algebra, it's really nice to see this come together as a matrix problem. So let's have a look at an actual example here. So we're given some data. They're ordered pairs formed from observations of 4 houses in a real estate market. Now, 4 data points is really small. It's not a sound statistical model to build. It's not sound to build a statistical model from 4 observations, but nonetheless, this will just suffice as an example to show the idea behind all of this. So the first value in each pair is the number of bedrooms in the house, and the second value is the current market value of the house in thousands of dollars, or in dollars, sorry, in dollars here. So this is, so we have 3,380,000. So this is a 3-bedroom house that has a price of $380,000, so current market value of that. Now, what we're trying to find is the regression line for the given data, and then we want to use it to predict a house with 4 bedrooms. So once we have, probably more than half a dozen points like this, we only have 4 here, but 4 or more is probably valid. Chances are we're going to have inconsistent data, right? In other words, we're going to have conflicting data, and we can see that directly here. So here's that inconsistent argument I was trying to make before. Here are 2 3-bedroom houses. Now, there are other differences we're not taking into account, other features of the house that aren't making it into this model. But this is leaving us with an inconsistent scenario, right? Each of these bedrooms, their first coefficient matches, or coordinate matches 3. However, their price does not, their y coordinate does not match. So this would automatically be an inconsistent system. So, we can see that just merely from that. The other way to see it would be this. As we change from 1 bedroom to 2 bedrooms, and we're thinking of this as a linear model, well, the growth and price from 1 bedroom to 2 bedrooms is the difference between $250,000 and $310,000. So we go from a 1-bedroom to a 2-bedroom house here, and the price increases by $60,000. So if we add 1 more bedroom, go from 2 to 3, then we would expect maybe a $60,000 increase, but this is a $70,000 increase, and this is an $85,000 increase. That is not a consistent step, right? So our slope doesn't match between each of these points. Again, so this is another argument as to this data being somewhat inconsistent as a system. And this is where the fact that these points are not collinear, as I said before, they don't all fit onto the same line because their steps between each other have steeper and less steep slopes than from one to the next. So we don't have a consistent system right here. And if we were to write it down as if we did, we could look at this situation right here. We could augment y to the matrix x to solve this, to try to solve this directly. And we'd see that, well, if I put this into reduced or row echelon form, this row zeroes out the first two columns of this row, yet we don't have a 0 over here where there's that 395 minus 380. We'd have 15, right? So that's going to, that would be 0, 0, 15. In that row, we have an inconsistent system. So there's where that non-collinearity makes this an inconsistent system. And chances are, if we have, you know, hundreds of points in the plane, you know, ordered pairs x, y like this, we're going to have lots of inconsistencies like that. So there's no hope of getting an exact solution. And we're always going to look for a least squares solution to this regression problem. So what I've done here, by the way, in the vector y is I've written my y components in units of $1,000. So 380 is of course $380,000. So, and that will interpret, we'll be able to interpret that easily at the very end when we come up with our actual model. So remember, the goal is this: we want to solve for beta naught and beta 1, my y-intercept beta naught and my slope beta 1 for this system x beta equals y, and we're going to do so in a least squares fashion, right? We're going to look for the least squares solution to this equation. Its least squares solution coincides with the solution, the exact solution to the normal equation, x transpose x beta equals x transpose y. So this is using our original method, not the QR factorization. Anything else, I think this, again, is the most direct way to do it. This is the normal equation. So x transpose x is here. This is x transpose times x, and then unknown beta naught beta 1. And then we have x transpose y on the right. And we just have to carry out some matrix products, right? We have to do x transpose times x on the left and figure out what this vector on the right is going to be. And that happens a couple steps from here. We get a 2 by 2. Remember, this is a 2 by 4 times a 4 by 2. So we have a 2 by 2 as the result here. It's nice and compact, times beta naught beta 1. And on the right-hand side, this product came out to a 2 by 1, right? With those two values as its entries. Remember, it's a 2 by 4 column or matrix times a 4 by 1 leaves us with a 2 by 1. So this problem actually gets packed down into a much nicer, smaller problem. And this will be the case no matter what when we're dealing with linear regression. We're just looking for beta naught beta 1. So that X matrix is going to be a something by 2. And we're always going to end up with a 2 by 2 when, once we carry out these products. Now, this part might be longer as well as this part, and similarly for the Y vector. But when we get to the solution, the system that we need to solve, it's always going to be a 2 by 2 like this, which is really nice and quick. So we can solve this system by inverting the 2 by 2 matrix, right? Since it is 2 by 2, it's almost, I think, just as fast to solve it with the matrix inverse. The inverse of this 2 by 2 is this matrix using the 2 by 2 inverse formula. So the vector beta is equal to A inverse times both sides of this equation. So beta naught beta 1, the vector beta here, is equal to A inverse times y. Or sorry, I guess I did call it A inverse, or A, none of those things are correct. It's this matrix inverse times this vector. We won't use names here. So that's what we have right here. Now, we carry out that product. The exact values are here, but those are not so useful for maybe having a look at what this line actually puts out as a value. So we round it to 2 decimal places each as follows. I know that might not be following significant figures well, but nonetheless, it's just an approximation model. And our regression line then is beta naught, our y-intercept is this entry, and then our slope is beta 1. So to make up beta naught plus beta 1x. So what we've now made is our regression line, or the line of best fit for these housing prices based on number of bedrooms. And that's now a predictive model, right? So now I can predict for any number of bedrooms. And I might want to check that it's more or less consistent. It's never going to be exactly equal to, maybe coincidentally, it could be once or twice exactly equal to, well, no, yeah, exactly equal to some of these values by plugging in 3 for the value x in here and getting whatever we get out of that. It'll probably be something at least reasonably close to $380,000, right? Again, it is the line of best fit. It's trying to capture the trend that the prices of these houses has, where, again, remember our output Y has unit in thousands of dollars. So just to test it out, we can do this. We can predict the value of a 4-bedroom house with this model. So we have x equals 4 bedrooms. So its value is 177.27 plus x equals 4, right? 69.55 times 4. This is in thousands of dollars, by the way. So this is this value plus this in thousands of dollars. So it's $177,270, $278,200. And when we add those together, this gives us a prediction of a 4-bedroom house at $455,470. And that at least meets the intuition that the 4-bedroom house costs more than the 3 bedrooms that we've seen, because it looks like as we increase bedrooms, right, we increase prices of the house. So it seems that this is probably capturing that trend in a reasonable way. Now, of course, 4 data points in a model is woefully small, but nonetheless, this gets the idea across. And it's unfortunately, I used a real estate example for this problem, but linear regression can be applied to many things throughout industry and finance and data science. Now, at the heart of so many machine learning programs, really, we have regression models like this, where machine learning is very much concerned with capturing the trend in data in order to make a prediction just outside of that data. So there's our example. This is the culmination of what we've done now in the course. So hopefully you'll see linear regression at some point in stat class, or at least find a use for linear algebra elsewhere in mathematics.